In this lecture, we want to talk about a brand new topic, and the new topic we're going to be just talking about is continuous random variables. So, if you think back to some of the previous lectures in this course, we talked about discrete random variables, right? So, a random variable is a value who's determined, or it's a variable whose value is determined by the outcome of a probability experiment. And so now we're just going to expand this topic to be talking about continuous. So, this is the new topic, continuous random variables. We're going to talk about what's called a probability distribution, and then we're going to end the lecture talking about the uniform probability distribution. Okay, so what's going on in this section? So in this section, we want to apply the concept of that probability distribution that we learned about for discrete random variables, all right, to continuous random variables. So remember, a continuous random variable is a variable or data that has infinite possible values. So we generally describe continuous random variables as measurements of some type. So, an example would be like how tall adult males are, or the time you spend waiting for a bus, things like that. So this concept of a probability distribution for continuous random variables is going to be much different than how we handled it for discrete probability distributions. So if you remember, for discrete probability distributions, the way we described them or showed them quite often was with a table. So the table listed the possible values of x and their corresponding probabilities. And we could do that because there was a finite number of possible outcomes. Well, here there's an infinite number of possible outcomes, so I can't set it up as a table. So what you're going to see in this lecture and in a bunch after this actually, is that we're going to use curves or graphs, okay, to describe the distribution or to show the distribution, and we're not going to use tables anymore. All right, so this is going to be the example that we're going to work to illustrate these topics. Okay, so suppose the United Parcel Service, UPS, is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Okay, so we're going to assume that it's for sure going to show up sometime between 10 and 11, okay? Not 9:51, not 11:01, sometime between 10 and 11. So, maybe it's a package you really want to get, so we're going to be like counting the minutes until that package comes, okay? So we're going to let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So basically what x is going to represent, if it helps to see it like this, is it's going to represent the time spent waiting for the package. All right, and we'll define it in minutes. Okay, so the delivery could come right at 10 a.m. Like the UPS driver could drop the package right off exactly right at 10 a.m. and then you would wait 0 minutes. Or the worst case scenario is, you had to wait until 11 a.m. and your wait time is 60 minutes. Okay. And what we're going to say then is, with all 1 minute interval of times between x is equal to 0 and x is equal to 60 equally likely. Okay, what I mean by that is to say that your package is just as likely to arrive sometime between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. Okay, so what's kind of hinting at here is this is a uniform distribution of wait times. Okay, because each interval there is equally likely. All right, so I'm going to ask a question next, okay? So, and then this question is going to help us understand some of the definitions that are going to come up on the next couple slides. All right, so what is the probability the package arrives sometime between 10 a.m. and 10:30? Okay, so just recall. You could wait between, let's say, remember 10 a.m. and 11 a.m. Okay, that's a 60-minute window. So now I want to find the probability, okay, that the package sometimes shows up between 10 a.m. and 10:30. All right, so what this means, if it shows up right at 10, you spent 0 minutes waiting, and it shows up at 10:30 you spent 30 minutes waiting. So I want to find the probability that the time you spent waiting is between 0 and 30 minutes, okay? So I'm going to give us the answer, and then I'm going to show you with some of the formulas and harder concepts in the rest of this lecture how we get this answer. So if you think about it, there's a 60-minute window. I'm saying what's the probability that it shows up in the first 30 minutes? Well, 30 minutes out of 60. The probability that it would show up sometime between 10 a.m. and 10:30. You could wait a total of 30 minutes divided by the 60 total possible minutes. It's just 1/2, okay? So now keep this in your mind, okay, as we go through the definitions and we know what the answer is. So as I introduce the definitions and some of the advanced concepts, we're going to all end up relating it back to this UPS example. Okay, so some definitions then. So the first one is what we call a density curve. And this is a curve that represents the distribution of a continuous random variable. So density curve, basically what it is, it's a graph. And by a graph, it's going to look like a curve, okay, that shows how the random variable is distributed. So if you think about it, going back when we did discrete random variables, we used a table, okay, to show the possible values of x and their corresponding probabilities. Here, instead of a table, we're going to use this concept, or what we call a density curve, okay? Density curve. Then we have what's called a probability density function, or you'll sometimes just hear me say, find the PDF, or what the PDF is. So in this class, a PDF stands for a probability density function, okay? So function, right, you know, from your previous math courses, is a mathematical relationship between two variables, or it could be more, but basically another way of saying what this probability density function is it's an equation used to compute probabilities. So we're going to use it to compute probabilities, like going back, like this probability right here, okay, for continuous random variables, and it must satisfy the following two properties, okay? The total area under the graph of the equation over all possible values of the random variable must equal 1. Okay, so if you think about it in probability, 1 represents, you know, 100% of possible outcomes. So in this case here, the area, all right, is going to go over 100% of the possible values. Okay. And the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. What that means is when we sketch these graphs in a little bit, it's never going to go negative. It's never going to go below the horizontal axis. So we have two definitions: probability density function, an equation used to compute probabilities for continuous random variables. And then we have this density curve. Now how they're related is the density curve is the graphical representation of the PDF. Okay, so the probability density function. So once you have the PDF, you know this probability density function. What you can do is you can sketch the curve, sketch the density curve. Okay, so how are we going to use these density curves in this PDF? First, as I said, you're going to, given a PDF, you're going to sketch its density curve. And then this is important. The second, how we're going to do it, is the area under the curve of the density function over an interval represents the probability of observing a value of the random variable in that interval. Okay, and it's going to be, you know, you probably are reading it on the screen and listening to me say it. You're like, what the heck does that mean? All right, the key concept here that's going to come up over the next few lectures is the area under the curve between two values is equal to the probability of the random variable x falls between those two values. So what's going on here? If you think back here, I want to find the probability the random variable x is between two values, in this case between 0 and 30. And what I'm going to do here is I'm going to find the density curve, okay, for this random variable x. And then the area under the curve between these two values should be the probability that I observe x between these two values. Okay. I promise you, and I know it seems weird in the videos, you know, watching this and then like, what the heck does all this mean? But I promise after you see the next example, me walking through it, the concepts of a density curve in a PDF will make a lot more sense. So just bear with it. Okay, so the random variable x can be any value on the interval from 0 to 60. That's why it's a continuous random variable. Okay, so this is what we know. The random variable x, I could wait between 0 minutes and 60 minutes. Think of this as the starting value. We'll call that a. And think of this 60 as the ending value. And we'll call that b, okay? Because any two intervals of equal length, okay, between 0 and 60 inclusive are equally likely, then what happens is when you have that, okay, any two intervals of equal length are equal probability, or equally likely, then we say x follows what's called a uniform probability distribution, okay? So what I want to do now is I want to describe this uniform probability distribution in terms of its probability density function and then what its density curve looks like. Okay. So what is the probability density function for a uniform distribution? Okay. So we just denote it with the f of x notation. Okay, that's the function notation. In this uniform distribution, all right, it's a piecewise defined function. Okay, so it's very simple. It's equal to 1 over b minus a. Okay, where does the b and a come from? Remember I said think of it as your starting value and your ending value. For x between a and b. And then when you get outside the possible values of a and b, right? Like you can't have any values below a or above b. We're going to say this curve, this function is equal to 0 otherwise. All right, so what does the density curve for this distribution look like? It's real simple, actually. So I'm going to draw the first quadrant of the Cartesian plane. Okay. Here's the value of x, so the value of the random variable. And along the vertical axis, we get f of x, okay, which is this function right here. And all it's saying is, between the values a and b, all right, this function is equal to 1 over b minus a. So between here, and here, it's just equal to 1 over b minus a. So it's just a flat horizontal line. And then once you get past b, it's just equal to 0. And once you get below a, it's just equal to 0. That's it. So it's just really just a horizontal line at 1 over b minus a. Okay? So f of x is equal to 1 over b minus a for x between a and b inclusive, 0 otherwise, and then it's the density curve is just this flat line. Okay, just this horizontal line here. Okay, so now let's go back to our example. Okay, this waiting for the package to come. Okay, so just recall for this, we're going to let x be equal to the time spent waiting, okay, for the package. And we know that x is going to be between 0 and 60. So like you can kind of start to see how this is coming together, okay? So there's the a and b. So my density function, my probability density function, piecewise defined function, it's 1 over b minus a. So it's 1 over 60 minus 0 for x between 0 and 60, and it's 0 otherwise. Okay, you can clean this up if you want. So it's just 1 over 60, because 60 minus 0 is 60, for 0 less than or equal to x less than or equal to 60, and it's 0 otherwise. All right. Now what does the density curve look like then? Okay, so the horizontal axis is x. And what is x? It's the time spent waiting for the package. And look, we know the possible values. It's between 0, here's 0, and here's 60. And then my f of x along the vertical axis is just 1 over 60. Okay, and this is not drawn to scale, obviously. Okay, and it's just going to be a horizontal line from 0 to 60. Okay, and then once you get past it, it's just equal to 0. It's just equal to 0 right there. So you just really have a horizontal line between the possible values, all right, and then it's just 1 over b minus a along the vertical axis. Okay, now remember, going back, the key concept here, okay, area under the curve between two values is equal to the probability the random variable x falls between those two values. So the next question, going back to what we had, what is the probability the package arrives sometime between 10 and 10:30? Okay, so that's the probability that you spend waiting between 0 and 30 minutes. To answer this now, you're going to use the density curve. And you're going to find the area under the curve between x is equal to 0 and x is equal to 30. So I'm going to resketch the density curve for you. So 0, here's 60, 1 over 60. Okay, so here's the thing. I want to be between 0, 30 is right between it. So I want to find that shaded area right there. In this area here, to find this area, this looks like a rectangle, okay? So how do you find the area of a rectangle? It's length times width. Well, the length to go from 0 to 30 is just 30. And the width is just this height here, 1 over 60. So 30 times 1 over 60 is 30 over 60, or 1/2. So look, going back, we said that the probability should be 1/2, right there. Okay, we did it intuitively, it makes sense. So now I just did this concept of a density curve in a probability density function to sketch the area and shade in what you're looking for, and that area is equivalent to the probability that you're trying to find. Okay, let's do another one, okay? All right, so as a follow-up, what's the probability the package arrives sometime between 10:30 and 10:45? Okay? Okay, well, if it shows up at 10:30, okay, how long did you spend waiting? You spent 30 minutes waiting. And if it shows up at 10:45, you spend 45 minutes waiting. So I want to find the probability that it's between 30 and 45. So again, what you're going to do is you're going to sketch the density curve and find area under the curve between x is equal to 30 and x is equal to 45. So x possible values are 0 and 60, and then the density curve was 1 over 60. So you want to be between 30, and then here's 45. Right there. So the area of this rectangle is length. So the length from 30 to 45 is 15. The width never changes. It's still 1 over 60. So this is just 15 over 60, or 1/4. So, you know, which is exactly makes sense because that's a 15-minute window out of an hour. That's 1/4 of an hour. So I hope this helps. I hope this kind of starting to make sense. All right, let's do another one here, a different example, so that you can kind of get another fresh take at this. Okay, so suppose the travel time from the White Plains Transit Center to SUNY WC on public transit. So I don't know how many people take the bus to school. I actually sometimes take the bus to school, and when I do, I take bus 40 from the transit center. So the travel time once you get on the bus, right, follows a uniform distribution with a minimum time of 12 minutes and a maximum time of 22 minutes. Okay. So here's what we're going to do. We're going to let the random variable x represent the time from White Plains Transit Center to SUNY WCC on public transit. Okay? And I'm telling you here that it follows this uniform distribution. So I'm going to let x equal the travel time on public transit. Now think about it. What did I say the minimum time and the maximum time was? So this value of x can only go between 12 minutes and 22 minutes. So right off the bat, you're seeing your A and your B, okay? And then I'm telling you then next that, or before I mean, that it's a uniform distribution. So you can start to see how it's going to fall into place. Uniform distribution. I know this is the formula for the probability density function, and this is what the density curve is going to look like. All right, so 3 questions. What is the probability density function PDF, all right, for this random variable x, the travel time on public transit? Well, f of x is equal to 1 over b minus a, so 22 minus 12. Okay, this is for x between 12 and 22 and 0 otherwise. So let's clean up 22 minus 12. So that's just 1 over 10 for x between 12 and 22 and 0 otherwise. All right, next, since we know it's a uniform distribution, let's sketch that density curve. So remember, x is the time spent on public transit. Okay, and the possible values are 12 and 22. So here's, 0, and then here's possible value 12, and then here's 22. And then the value of the density function is 1 divided by 22 minus 12, or just 1/10. Here. So now what is the probability the travel time is between 15 and 18 minutes? Well, go to your curve, shade in the area you're looking for between 15 and 18. So that's a rectangle, right? So the area is the length, which is the distance from 15 to 18, which is 3, times the width, which is this value here, 1 over 10, So 3 times 1 over 10 is 3 tenths. You can even write it as 0.30. So I hope this helps kind of understanding the concept of what a density function is, or density curve and a probability density function is, class. And the two examples. In this case, they both involve time, but the concepts were, similar or exactly the same across the two.